Hello again. In this session, we will discuss friction. Now, you probably already know what friction is, but we will now discuss friction under the light of what we have recently learned. Now, you know that you see friction in play whenever you try to slide something over a surface. So, friction acts whenever there is a relative motion between two surfaces. So if you think about it, friction is again a contact force. But how does it differ from normal? Normal reaction always acts perpendicular to the surface of contact, whereas friction will always act along the surface of contact. So, you could say that the total contact force that a surface or a body exerts on another body has two components. One which is perpendicular to the surface and one which is along the surface. The component which is perpendicular to the surface is called normal, and the component which is parallel to the surface is called frictional force. Now, the frictional force, it has been found, has a direct relation to the amount of normal reaction. That is, this horizontal component of the contact force actually depends on the vertical component of this contact force. It has been found that friction, the amount of friction that a surface offers, is directly proportional to normal reaction. Right. So, let's try to understand friction by taking a very simple example. Let's say there is a block lying on the floor. Let's say you know that the minimum force required to move this block is 80 Newton. So, unless a force of greater than 80 Newton is applied, this block will not move. Right. So, let's say that a force F is applied on this block and the ground offers a friction which is F, small f. Let's not use the subscript S for now. You'll later understand why. So, let's denote friction by small f. So, capital F is the amount of force that we are externally applying, and small f is the friction which the surface is offering. So, let's draw a plot between the force applied and the friction offered. Right. So, now let's first tabulate this. First of all, at the point where there is zero force applied, what do you think is the friction offered? Well, if you apply zero horizontal force, the ground will not offer any friction. Because if you think about this block, let's draw its free body diagram. We have the weight of this block acting downwards, mg. Then we know there would be a normal reaction from the ground which will act vertically upwards because the contact is horizontal. Then we have an externally applied force F and a friction which acts towards the left. Now, in a case where F is 0 and friction is not, the block will start to move. Now, you know that this can never happen. The ground can never cause the block to move by friction. Friction only acts to oppose relative motion. And if such a thing happens where friction itself starts motion, then it would contradict its behavior, because friction acts to prevent relative motion. It will never act to start it, right? So, when the external force is 0, the frictional force is also 0. Now, if you raise this force up to 10 Newton, what do you think is the amount of friction acting? Now, the frictional force that can be offered is up to 80 newtons. But do you think the entire force will act? It certainly won't, right? Because if on a force of 10 Newton, if a 80 Newton friction acts, once again we would see the friction causing relative motion. And it by nature does not want any relative motion. So when the external force is 10, frictional force will also be equal to 10. So it has a capacity to go up to 80 newtons, but it will not, because there is no requirement for that. Right. So let's take another value. Let's say if there was 40 Newton of external force, then the frictional force would be 40. The case would go on up to 80 newtons. Till you apply 80 Newton, the frictional force offered is exactly equal to the external force applied. So if I try to plot this on a graph, you would see that this is a line where x is equal to y. So you can come back to graphs once you have studied coordinate geometry and you have got a very good idea of that. So for now, I'll plot the graph, but if you have any confusions, you should revisit this section later. So, till the force is less than 80, you would see a straight line which rises with a constant slope. So this basically shows that whatever is the value of force, same is the value of friction. Now, if you were to increase this force, that is, as soon as you make this externally applied force greater than 80, let's say the value is only made to 81. Now what happens is, this value of friction drops slightly and then becomes constant. So let's say, I'm just taking numbers to explain this, let's say the force drops to 79. So right after 80, the force will drop slightly and then it would become constant. What this means is that after an increment from 80, no matter how large a force you apply, whether it is 100 or whether it is 1000, the frictional force will remain 79 newtons. Right. So you can clearly see this is the maximum value of friction. Right. So now, let's see why this change comes. You can see that up to 80 newtons, the block was stationary. So the friction that was acting was static friction. So this was static friction. So for less than 80, the force less than 80, you had static friction, which basically means that the object was still stationary. There was no relative motion. So static friction acts when there is no relative motion, right? And then as soon as the motion starts, the friction drops slightly, because then the friction that acts is kinetic friction. So kinetic friction acts, in this case it is for more than 80, it acts when relative motion starts. So once the object starts to move with respect to the surface, the friction changes from static to kinetic and its value drops slightly. Right. So far we have understood that frictional force acts to oppose a relative motion, and we saw that frictional force depends on normal reaction. We also saw that it will always act along the surface of contact. Right. So now you know that to remove proportionality we have to add constants. But friction we have seen is of two kinds, static as well as kinetic. So the static friction is equal to mu static times normal reaction, and kinetic friction is equal to mu kinetic times normal reaction. Now let's first start with kinetic friction. In this case, we know that kinetic friction has a single value. This means that once the motion starts, the value of kinetic friction does not change. So kinetic friction starts to act once the motion starts, and once that happens, there is only a single value of friction that will act. So kinetic friction is constant and its value is equal to mu kinetic times normal. This mu k or mu kinetic is the coefficient. This mu k is called coefficient of kinetic friction. So mu k is the coefficient for kinetic friction. Right. So that is about kinetic friction. Let's now come to static friction. Now static friction, you can see from this graph, does not have a single value. It acts as per the demand, right? If the demand is less, its value is lesser than its maximum value. But it does always have a maximum value, right? Like we saw in this case, it was 80 newtons. So similarly, when we write this equation that Fs is equal to mu s time normal, this is actually the maximum value of static friction. Once again, this is because static friction can take any value from 0 up to the maximum as and when required. So when we write this expression, please notice that we are talking about the maximum value of friction, the maximum value of static friction. So the maximum value of static friction is mu static times normal reaction. So mu s here is the coefficient of static friction. Right. So friction opposes relative motion. It acts along the surface. It is proportional to normal reaction, and it is of two different kinds depending on whether or not motion is started. If it is started, the friction is kinetic friction, which only has a single value. And if the motion is yet to start, the friction is static friction, and it would act in the right amount to prevent motion. Right. Now, as we can see from this graph, the static friction, the maximum of static friction is always more than equal to the kinetic friction. So the maximum of the static friction is always more than or just equal to the kinetic friction. And we can infer using that relation that the coefficient of static friction is also always more than equal to the coefficient of kinetic friction. Right. So the coefficient of static friction is always more than the coefficient of kinetic friction. Right. So once we understand this, let's take a simple example and implement this. So let's say you have a block of 100 newtons of mass 10 kg, and it is lying on a surface which has a coefficient of friction given by 0.5. So when you're given a single coefficient, you can assume only in such cases that mu static is equal to mu kinetic, and that is given to be 0.5. So this block is lying on a surface which has coefficient of friction of 0.5, and this is acted upon by a force F which acts at an angle of 30 degrees. Right. So what we have to find is the minimum value of F for this motion to start. Right. So to do this, once again, we have a problem involving forces. So we'll start the procedure we had defined. The first thing to do always is to identify the system. Once again, we are dealing with a simple case where we have a single block, and hence it's very easy. It's a very easy choice that 10 kg is our system. Once we have decided the system, the next thing to do is to list down all the forces in a free body diagram. So let's do that by drawing 10 kg mass as a single point. Now, the forces which are acting on this block are a 100 Newton force, which is its weight acting downwards. Then we have a force F acting at 30 degree with the horizontal. Then you obviously have a normal reaction from the ground, since due to its weight, the block must be pushing ground. And finally, you have friction. Now the direction of friction is to be decided by looking at the direction of impending motion. In this case, you can see that this block has a tendency to move towards the right? So whenever you have to decide the direction of friction, first assume that there is no friction. Then see the direction in which that block has a tendency to move. In this case, in absence of friction, this block will clearly move towards the right. So we know that the friction will act in the opposite direction. That is, it will act towards the left. So we know that friction will act in this direction and will denote it by the symbol small f. Now once again, you can see in our list of procedures, we have a force which is not aligned with the axis, right? Once again, the obvious choice of coordinate axis is horizontal and vertical, right? So once again, what we will do is we will break the force into two components, one which is horizontal and the other which is vertical. And in this case, the angle is being made with the horizontal axis. So once again, we'll have the cos component in the horizontal. So this component will become F cos 30 degree, and the vertical component would be F sin 30 degrees. Right. So once we do that, we have a simplified free body diagram which looks something like this. You have normal, then you have F sin 30 degrees. When there are horizontal forces towards the right, you have F cos 30 degree. To the left, we have friction, and downward force is the weight, which is 100 Newton. Now, we are trying to find the force which just starts the motion. Like, let's get back to our example, the example we had done to understand this. So we know that at 80, there was just a balance, right? The final equilibrium. So even if the force was increased to 80.00001, the motion would have started. So we could say that the minimum force to start the motion is exactly 80, right? Because even if it is slightly more than 80, the motion would start. So it is okay to say that 80 is a critical point, right? So in this case, when we want the motion to just start, we would say that the horizontal forces are balanced, but at the final equilibrium, at the tilting point, the friction would be the maximum possible static friction, right? Because as you keep increasing F, the value of friction, the value of static friction will keep increasing. So at the tilting point, the friction must be acting at its maximum possible value, right? So once again, in our list of procedures, the next thing to do is to write the equations for x and y separately. So let's do that. Let's first write the equations for x and then for y. For the equations in x, we see that F cos 30 degree. Now cos 30, I hope you know, is root 3 by 2. This is equal to static friction maximum. So F root 3 by 2 is equal to the maximum of static friction. And from the vertical forces, we see that normal plus F sin 30 degree. Once again, sin 30 is half. So we have N plus F by 2 is equal to 100. Right. Now, Is there any other relation that we know of? Because we can clearly see that these two equations have three variables and we only have two equations. So whenever we need to solve a system of equations, always check that the number of variables should be equal to the number of equations. If you're short of equations, that means you should be looking for another relation. Right. So what is that missing relation? Can you think of it? Well, that relation is that the maximum value of static friction is mu times the normal reaction. So Fs max is equal to mu times, mu is 0.5 times the normal reaction. So this is the first equation, this is the second equation, and this one here is the third and final equation. Right. So let's now start solving this. The simplest way to solve this is to substitute Fs max in the first equation. So doing that, you would get that F into root 3 by 2 is equal to n by 2. Now 0.5 is half, so I've written it as n by 2. The second equation is that n plus F by 2 is equal to 100. Now, to solve this equation, what you should do is cancel these two on both sides. So now you have F root 3 is equal to n, and if now I add these two equations, let's call this 4 and 5. After making this change where I've cancelled this 2 with this 2, I have F root 3 equal to n and n plus F by 2 equal to 100. So if I add these two equations, I see that normal gets cancelled from both sides, and that leaves me with the equation that F root 3 plus F by 2 is equal to 100. So root 3, I've told you earlier, is 1.7. So what I'm doing is I'm taking F common out of these two terms. So what I'm left with is 1.7 plus 0.5 is equal to 100. So this gives you that F is equal to 100 divided by 2.2. So you can further simplify this by yourself, but this is the amount of force, the minimum force that is required to start the motion of this block. Right. So with this, we finished the discussion of friction. So let's look back at what we have learned. The first thing that we learned is that friction acts to prevent relative motion. It always acts along the surface. Its magnitude is proportional to the amount of normal reaction there exists between the two surfaces. And then friction is of two types, static and kinetic, depending on whether or not motion is started. We saw that static friction can take any value between 0 and the maximum possible value. And this maximum possible value is slightly more than kinetic friction. Also, for kinetic friction, we saw that kinetic friction has a fixed value which does not change once the motion starts. Right. So with this, we come to the end of this session. In the next session, we will solve a few problems based on all the forces that we have learned so far.